you had that question.
For this Timosenko beam element, for using interdependent interpolation, you told me about the K matrix. Okay, but I was trying to understand with the reduced integration.
No, you won't get the same thing with reduced.
No, I'm not with this. Through Jane Reddy, I was trying to get, but I was not able to understand.
So I had done that no, in the class itself.
No, sir, you have not done.
No,
Reduced integration.
I had introduced. No, I had introduced. Then I said this shear energy part. You do the integration with numerical integration using 1 point.
This one after that.
So see, you have originally we started with Timosenko beam. So when we gave this. So you have if you axial part if you take out, then this bending part. So this you integrate exactly. This you do the 1 point integration. This integration, so that whatever is stiffness. Parallel to coordinate axes. Yeah. So, in case of triangle, you need not have, that was for rectangles. So, if you are using rectangles, so I will actually answer this question. So, are there any other question? So, actually one question was about, no, so I was talking about basically two dimensional elements. So, we talked about formulation in physical coordinate space. So, here then again we said we can have triangles and we can have rectangle. In case of triangle, when you are doing, so the it is not necessary that the common edge shared by two elements should be parallel to either x or y, because that is not possible, because maybe one edge can be still for triangle the inter-element compatibility is actually satisfied. So, let us say we have this triangle and then there is another adjacent triangle, let us say this, and here it's a 3-noded triangle, even it can be a 6-noded triangle. So, within these the temperature approximation is linear. Say for here you might write, let us say this is the ith triangle and this is the jth triangle in terms of global numbering. So, for this the temperature field is given by A0I plus A1I x plus A2I y, and for this the temperature field would be given by T equal to say A0 j plus A1 j. I am just using a different notation for these constants, so just to differentiate, the form of the interpolation is same, and A2j y. Now, when we now what we are saying that in the within the first this ith element, the interpolation of the temperature is given by this, and in the jth element the interpolation is given by this. Now, the continuity demands that when we evaluate the temperature distribution along this common edge shared by these two elements from this side or this side, the temperature distribution must be unique, that is same. Already at the time of assembly we would be saying that at this node, whether belonging to this element or this element, the temperature is same, that is both the elements are sharing the common node and same degree of freedom, that is temperature value. Similarly here, so the temperature value, whether it is at this node evaluate from the first element or from the second element, it is going to be the same, I and j. Now, in between what happens? So, since when you are moving along a particular edge, this is a straight line, so the equation of this straight line is going to be y equal to, that is what we had said, A0 plus A1 into x. So, when you want to evaluate, say now the temperature distribution along this blue line belonging to the ith element, in this expression you put y equal to A0 plus A1x. When you do that, this will still be a linear function in x. So, linear function in x means those constants can be expressed in terms of the temperature value here and temperature value here. Same thing when you evaluate the temperature distribution along the line belonging to the jth element, you will use this expression. You will again write your y in terms of x. So, the resulting expression is again going to be linear in x. Linear in x means those constants can again be written in terms of the temperature value here, temperature value here. So, and since the temperature value at this point and this point is same for both the elements, so across the line, whether you evaluate the temperature from ith element or jth element, the temperature distribution would be same. That means we get a continuous distribution of temperature, there is no jump in the temperature when we go across the common boundary from one element to another element. So, for the triangle it does not matter. Same way you can check that if you are using a 6-noded triangle, then also you will satisfy the inter-element continuity requirement of the field variable, in this case temperature. But then when we go for the quadrilaterals, so what I had mentioned was that in case of quadrilateral we need to have a rectangle. So, as long as we have a rectangle, whether it is a 4-noded rectangle or an 8-noded rectangle, so this is say one rectangle and this is another rectangle, and with these edges parallel to coordinate axes. So, this is say x and this is y, and now this is the common edge, and let us say that the elements of 4-noded one. So, these are 4 nodes of the element, again this is say ith element and this is your jth element. The temperature field, when you look at by within each, it is going to be like T equal to A0 I plus A1 I x plus A2 I y plus A3 I x y. Now, in this expression, similar expression will be there for the jth element, the interpolation within the element. Now, in this element, when you want to evaluate the temperature along this line, so since this edge is parallel to y, so x is going to be constant. So, in this expression, if you put x as a constant value, this function would be linear in y. Once it is linear in y, so whatever constants you get in this, that those can be written in terms of the temperature value at this node and temperature value at this node. Same will hold good for the jth element as well, and that therefore, since the value of temperature at this point and at this point is same for both the elements, so you will get the same distribution along this line, whether you evaluate from this element or you evaluate from this element. So, but now this is when these edges are either parallel to x or y, the coordinate axes. That means the element must be a rectangle and the edges must be parallel to coordinate axes. Now, let us say that the element is general quadrilateral and see what happens. So, now I have x y like this, but the elements are general quadrilateral. So, one element is, let us say, like this, and the another element is say like that. Let us say these are the two elements, this is ith element and this is jth element. So, again say 4-noded elements. So, these are the nodes of these elements, and now see when you want to evaluate the temperature distribution along this line, either from this element or this element. Now, this is again a straight line, of course. So, x and y are going to be interrelated. So, I can again write for this line y equal to some equation of a straight line A0 plus A1x, and now this kind of an expression, when we substitute, now the temperature distribution is similar within the element, that is given by that. So, when you put here, you will see that the last term x into y will give you a x square term. So, the resulting expression for temperature along this line will be quadratic in x, and what you are having as common temperature values is only the temperature value at this point and the temperature value at this point, but the variation of temperature along that line is quadratic. So, it requires actually 3 values. If we know 3 values along the line, we can fit a unique curve, but since here we have between these two elements common values are only 2, that is one at this node and one at this node. So, obviously, we have quadratic variation obtained from this element in general would be different from this element. So, that means when you if I plot the temperature obtained along this line from the ith element and from the jth element, this temperature distribution is going to be different. So, you get a jump when you move across the common edge. So, this does not satisfy the continuity requirement of the field variable, that is temperature in this case across the elements, when the edge is not parallel to either x or y. So, for the triangle that is not required. So, the question asked was in case of triangle how it happens. So, in case of triangle there is no problem, the edges can be inclined with any at any angle with x or y, still you satisfy the continuity requirement. So, the triangle can be formulated in physical coordinate space satisfying the inter-element compatibility requirement, but if we want to do the formulation in physical coordinate space considering quadrilaterals. So, then the quadrilateral has to be actually a rectangle with edges parallel to x and y, then only we can satisfy the inter-element continuity requirement of the field variables. Okay. So, is there any other question? Yeah. Right. No, it is not connected, but still no, you have a corresponding degree of freedom there. So, you have a one additional term in the approximation. So, it is a better approximation compared to 8 noded element, although the performance would be marginally different, the convergence characteristics, but it is better than 8 noded because you have an additional term in the approximation within the element. So, the question was about difference between 8 and 9 noded. So, because we will have an additional term in the approximation for the field variable. So, its convergence, that is when you solve a certain problem, you need to discretize into a number of elements to make sure that if you further increase the number of elements, the results do not change. So, that number which is minimum required to get the accurate solution would be less for a large size problem in case of 9 noded element compared to 8 noded element, because it has an additional term. So, it approximates the temperature more accurately within the element. Okay. So, are there any other questions? So, then one more question was about the reduced integration. So, what I had talked about before the mid semester break about the reduced integration. So, for the Timoshenko beam element, if you have linear interpolation for both say transverse displacement B and theta z, and as I said that if it is used for solving thin problems, there is a shear locking, it actually underestimates the deflection. So, then you have energy bending part of the strain energy and the transverse shear strain energy. So, rather than stiffness contribution from transverse shear strain energy, rather than doing the exact integration of that term, you do the integration with 1 point numerical integration. So, that is what is known as reduced integration. So, that was another question. So, whatever formulation you have for 2 noded Timoshenko beam element, the shear energy, rather than exactly integrating that, you actually use the numerical integration with single point integration, and whatever then stiffness, total stiffness after combining the bending and shear, whatever you get, if you use that, then it will not give locking problems, but then that can only be used for thin problems. For thick problems, it will actually underestimate the stiffness and therefore overestimate deflection. So, that is the problem with reduced integration. Maybe we will discuss this when we also will be discussing about some plate bending problems. So, that time we will discuss more about this. So, let me continue with the formulation in 2D. So, last class what we had started is 2D heat conduction. So, I had derived the governing equation. So, first I said that let us consider a rectangular domain, although actually domain can be any arbitrary domain. So, and a bit let us say that you have some coordinate axes, need not be at the corner, they can be anywhere. And so, for this edge x is equal to x1, for this edge x equal to x2 and so on. And we had derived, so finally what was the governing differential equation for this problem was minus del by del x of k into del t by del x, of course assuming that the material is linear and isotropic. So, thermal conductivity is independent of temperature. So, it is a linear and thermal conductivity is same in all the directions. So, therefore, it is isotropic. So, del by del x of k into del t by del x minus del by del y, this we had derived in the last class, and minus qz is equal to 0 or equal to qz. So, this was the differential equation we derived in the last class. Now again, if we want to solve this differential equation using again finite elements, so the first step would be say getting the weak form or the corresponding integral functional, then appropriate interpolation of the temperature field within the element, say triangle or quadrilateral rectangle, or maybe when we look at the natural coordinate formulation. So first we will look at the formulation of a triangular element for this problem. So first is the weighted residual statement. So these steps you would see are same actually for all problems. So weighted residual statement WRS. So what you do is, now the domain is two dimensional. We are assuming that nothing changes along the thickness. So we need not worry about the thickness part here. So weighted residual statement is going to be the integration over the entire domain, and since it is rectangle, although we can use any arbitrary domain, but for the timing to understand the concepts I am using the rectangular domain. So this is x1 to x2 and y1 to y2. So what I am saying is, this edge is x is equal to x1, this edge is x equal to x2, and similarly this edge is y equal to y1 and this edge is y equal to y2. That is, the edges are parallel to x and y. So the integration is along two dimensional domain from x1 to x2, y1 to y2. Weight function say w, and then this residual, which is this entire quantity. So minus del by del x of k into del t by del x minus del by del y of k into del t by del y minus qz dx dy is equal to 0. So this is your weighted residual statement, and we want to get the idea about the primary variable, secondary variable, and so on. So we want to do the integration by parts. Now when you want to do the integration, actually what you can do is, you can directly use what is known as divergence theorem, but I am again doing it from the basics, assuming that the domain is rectangle, and then demonstrate you the same kind of expression what we get using the divergence theorem. So now the first term, if you look at, which is minus w del by del x k into del t by del x. So here the derivative of this term is second derivative with respect to x. So if we do the integration by parts for this term with respect to x, we can shift the one derivative from this temperature to weight function w. So we will have, so now here we want to do the integration with respect to x for the first term. So first term, that is, which is usually the boundary term, will be, you are doing the integration with respect to x. So this into integration of this term, so that will give you minus sign, of course is there. So minus w and integration of this, which will give you k into del t by del x. But the integration with respect to y will actually be there. So that is integration with respect to y here, and this expression is evaluated at x1 and x2 dy. So this will be the first term. We are doing the integration by parts with respect to x. So y integration remains. So this is first function into integral of second, so which is del by del x, and in the integral cancel. So you get k into del t by del x. And since this is a definite integral from x1 to x2, so you will have to put the limits from x1 to x2, and the y integration remains same. Then the second term would be minus minus plus, and the integration from x1 to x2, integration from y1 to y2, derivative of this, which will be del w by del x, integration of this, which is k into del t by del x dx dy. So this is what you will get if you do the integration by parts with respect to x for the first term. So one, you get the boundary term, which is at boundary x equal to x2 and x equal to x1, and another is the domain integral. This is what usually we used to get in the 1D problems. So then similarly take the second term, so w into now del w by del y into k del t by del y, second derivative with respect to y. So for the second term we do the integration by parts with respect to y. So when you do that, so again the first term, the integration with respect to x would remain. So let me put here plus integration from x2 to x1 to x2 would remain there, minus w k del t by del y, this whole expression evaluated at y1 and y2 dx. Now here it was dy, here it is dx for the second term. Now that is, we are looking at this term, and then minus minus plus, the integration both will remain y1 to y2 and x1 to x2, and then you have derivative of w with respect to y now, because we are transferring this derivative, and k into del t by del y dx dy. So this is the second term. So integration by parts for this, this is what you get. The last term is of course your forcing function, so that remains as it is. So you have minus integration, let me write that separately, integration y1 to y2, x1 to x2, w qz dx dy is equal to 0. So this is what finally you get when you do the integration by parts for the first term with respect to x, for the second term with respect to y. Now let us do little bit of interpretation of these boundary terms. So if you look at, let me go, now if I want to represent the boundary terms by a single integration along the boundary of the domain. So say I start from here, so go in an anti-clockwise fashion. So from here to here, then from here to here, and then from here to here, and then from here to here. Because now if you look at all the these are two boundary terms, and these are also two boundary terms, the second one here, and they are covering actually all the four boundaries of the domain. So what I can do is represent that by a kind of a boundary integral term, which is covering the entire closed boundary of the domain. So for that, if you look at the interpretation, so let me look at the first boundary. First boundary is actually your y equal to y1. Y equal to y1 term is sitting here, that is in this, which is lower limit. So if you look at this particular term here, at lower limit, because when you write this value of this whole thing at y equal to y2 minus value of the whole thing at y equal to y1, so minus minus would become plus. So at lower boundary you will have this term as wk del t by del y evaluated at y1 integration of course x1 to x2 dx. So now what is this k into del t by del y for that boundary? See, k into del t by del y would give me the heat actually the flux in which direction, plus what you get is minus minus, it becomes plus. So k into del t by del y will give me heat flux in negative y direction, and that negative y direction is actually my outward normal here. So if I denote that outward normal by n, so I can say that's nothing but actually qn. So for this boundary that is at y equal to y1, my k into del t by del y is giving me qn, which is flux going away from the boundary, that is basically along negative y direction, because flux in the positive y direction would be minus k into del t by del y. And then so I can write that integration. So this is essentially gives me a heat flux along this direction, and of course the integration is starting from here up to here, because the integration is from x1 to x2. Then if I look at the interpretation for this, where you have x equal to x2 and x equal to x2 is going to come from this term, and in that term what you have is, see again this upper boundary, so you have minus wk del t by del x and x1 to x2 dy. Here the outward normal is, for this the outward normal is along the plus x direction itself, and so if you look at this term here minus k del t by del x actually is giving me the heat flux along the outward normal to this particular boundary of the domain. So again I can write that as this term as minus k into del t by del x as actually qn, so it would become simply wqn, and then of course the integration from here to here. So I am going in the same direction, that is integration from here to here. Then when you come to this boundary, are you following what I am saying? So similarly when you come to this, that is y equal to y2, and that term boundary term is sitting here, that is minus wk del t by del y evaluated at y equal to y2, the integration is from x1 to x2 dx. See, now for this boundary the outward normal is along the positive y direction, so minus k into del t by del y will give me the heat flux along the outward normal to this particular boundary. So that means I can replace minus k del t by del y as qn. Of course, n is actually y, that is n is along positive y direction for that boundary, and then this integral again would become, and of course another thing you would see that this integration is actually from this point to this point in that direction. So, but now to move along the anti-clockwise direction I would be moving in this direction. So, if I use a different coordinate for the integration, so the increment in that would be minus of this, and the limit again is, so this integration is from this point to this point, and then when we are going in a cyclic order we have to change the integration from this point to this point. So, 2 minus would cancel each other. So, again it would become actually integration w qn and say a path coordinate ds. So, similarly you can argue out about this. So, finally what I want to say that all the 4 boundary terms together can be written as a cyclic integral. This integral means along the closed boundary, and weight function w into qn ds. ds is a essentially path coordinate is along the direction of integration. So, say this point is s equal to 0, then you are going from here to here, and then again s is varying from some value to some value here, and then s is varying from some value from here to here. So, actually a distance, s is a distance coordinate you can say. So, I can write this as w qn ds. The other terms remain same, that is this term and this term, they remain same because they are domain integrals. So, I can write the two together, say x1 to I am writing y first. So, this integral is y1 to y2, x1 to x2, and we can put both these terms together. So, we will have del w by del x k into del t by del x and plus del w by del y into k into del t by del y dx dy. That is I am just writing this term and this term. Okay. And then the last term of course is this, which is also domain integration, minus y1 to y2 and x1 to x2 w qz dx dy equal to 0. So, other terms remain same, only thing we have done is actually this. So, where now this qn we define it to be qn is equal to minus k into del t by del n, that is rate of change of temperature along outward normal. And now with this expression you can actually again reinterpret back all the 4 terms, boundary terms which we have here. The way I explained, now you can get all these 4 terms by expanding this, expressing this cyclic integral, closed contour integral along the entire boundary of the domain. So, it is actually ultimately this expression is valid irrespective of whether the the boundary is actually rectangular boundary or any arbitrary boundary. So, you will always you can always write this term in this fashion, the boundary integral term. So, this is your weak form for the problem. Again we can do interpretation about the primary and secondary variables. So, as you see this is the boundary term, this is the only boundary term, and that is coming as a product of weight function and this qn. So, if we think of replace weight function by t, that is what is our primary variable. So, obviously this is a second order differential equation, partial differential equation. So, obviously the temperature is going to be the primary variable, which is clear from this that only in the boundary term w is there, no derivatives of w. So, the primary variable is only t, and that must be continuous across the element boundaries, that is what we said, and should be degrees of freedom at the nodes. And then corresponding to this we have this qn, which is the heat flux along the outward normal to the boundary, and that becomes your secondary variable. So, from this you can say that the primary variable of the problem is t, and corresponding secondary variable is qn, which is minus k into del t by del, this is n, outward normal, that can be x y or minus x minus y depending on the boundary in this particular case, or it can be at some angle with x and y depending if the boundary is arbitrary. The next thing is of course we can develop the element level governing equation from this itself, or we can go to the integral functional, both ways you can do. So now we want to obtain integral functional. So for obtaining the integral functional, what you do is take W as variation in T, that is delta T. W is, because this is coming from the heat flux, the corresponding variable is temperature, so the W can be interpreted as variation in delta T. So with W as delta T here, and then if you take out delta variational operator as common, so what you will get is you can see we have these steps are identical to what we discussed for 1D problem. So in this W is delta T, delta when you take out this term in the functional will simply give you T into Qn ds, the integration along the contour along the outer boundary of the domain. Then if you look at these two terms, this would become del by del x of delta T, if you look at this, and of course as we had discussed earlier that variation and the differentiation can be interchanged, so that can as well be written as delta of del T by del x. So you have basically this term would be like delta of del T by del x into k into del T by del x, and if we take delta common out, we can write that as half of k into del T by del x whole square. So that is going to contribute finally, so plus we have this domain integration y1 to y2 and x1 to x2, and let me write that half here, and k is also now I can take common, so what you will have is del T by del x whole square plus del T by del y whole square for the second term, and then you have dx dy, and then the last term is your this particular term, which will be minus again integration y1 to y2 x1 to x2 and t into qg dx dy. So your integral functional is going to be this, corresponding to this problem. Okay. So this is of course this integration is over the entire domain of the problem. So once we have this, then now we can think of formulating a finite element. So we'll have to first now say 2D problem, we'll have to choose the shape. So let us talk of 3-noded triangular element formulated in physical coordinate space. So let me take a example of a 3-noded triangular element. So what I am going to do, first I will just develop the shape functions and then the element level governing equations. So let us say that now we have this triangle with edges arbitrarily oriented with respect to x and y, and now I am actually I can use the common coordinate, and so say xy, a global coordinate system, and let us say that the corner nodes are local node numbers 1, 2 and 3, and the coordinates of this node are, let us say, x1 y1, coordinates of this node are, let us say, x2 y2, and coordinates of this node are, say, x3 y3. And maybe let us say we have some point P here within the element whose coordinates are x and y, general xy within the element. Also, since T is a primary variable, it must be continuous across the element boundaries. So the first requirement for that is that T must be degrees of freedom at the node points. So you should have as a degrees of freedom T1 here, value of temperature T2 here as a degree of freedom, value of temperature T3 here as a degree of freedom. So now for each node we have 1 degree of freedom, that is temperature, and for the element we have 3 degrees of freedom T1, T2, T3. So elemental degrees of freedom are 3. So this is the first thing. Now when we assume this form of the shape of the element, 3 nodes, the degrees of freedom and everything. So now we can write the expression for T within the element, which is the approximation of the temperature, that is field variable. Say we can say A0 plus A1x plus A2y. So this is what you can have, linear in term, constant term, linear in x, linear in y terms. As usual, like we are doing in case of 1D problems. We then express this A0, A1 and A2 in terms of the values of the temperatures at the node points, that is T1, T2, T3. So I can say that value of T at x1, y1 is equal to T1. So I can say one equation, T1 is equal to A0 plus A1 x1 plus A2 y1, that is values of x and y at first node. Then at second node, that is where x equal to x2, y equal to y2, the temperature T equal to T2. So I can say T2 is equal to A0 plus A1 x2 plus A2 y2. Similarly, for node 3, I can say T3 is equal to A0 plus A1 x3 plus A2 y3. Now see what we want to do. We actually want to express this A0, A1, A2 in terms of T1, T2, T3. So the unknown constants in the approximate solution we need to express in terms of the degrees of freedom. So essentially we have to solve these three equations simultaneously. So let me symbolically write that. So if I put all of these T1, T2, T3 together as a vector, and this side let me write the constants on the as a vector on the right hand side. So I can write this as A0 plus A1, I mean A0, A1, A2 here, and then here what you have in the first equation 1, then x1, y1, then 1, x2, y2, 1, x3, y3. These three equations can be written like this, isn't it? This is straightforward. So T means this into this gives you T1, and second row into this vector gives you T2, and so on. And let us say that we use some notation. So this is nothing but vector of elemental degrees of freedom. So we say that this is our D, and let me give some name to this. Let me say that this is a P matrix, and this is of course the same set of constants. So that let me retain A0, A1 and A2. We can write like this, where the P is defined by this and D is defined by this. Now because I want A0, A1, A2, so I can write this as A0, A1, A2 is equal to P inverse into D. I can do that, right? Of course, you will have to evaluate this P inverse. So that is inverse of this 3 by 3 matrix, that needs to be evaluated. Now once you have this, finally we want to write the approximation for T in terms of actually DE. So I can then write T also, what we have assumed here. This also I can write as in terms of 1 x y, and then here A0, A1 and A2, isn't it? It's the same thing, A0 plus A1x plus A2y, and from this equation we have got A0, A1, A2 in terms of P inverse and DE. So I can say that this is 1 x y, then here I have P inverse, and then here I have DE. And if you look at this 1 x y is 1 by 3 matrix, P is a 3 by 3, so its inverse is also going to be 3 by 3, DE is a 3 by 1 vector. So if you multiply the first two, because this is anyway is the vector of elemental degrees of freedom, this is in terms of course the coordinates x y, and this is in terms of the nodal coordinates x y coordinates of node 1, 2, 3. So I can multiply these two. So 1 by 3 into 3 by 3 will give you 1 by 3 vector, and so that we call as shape functions. So let us say there is a specific name given to these shape functions because of their interpretation. So let me use here the notation for the shape functions as L1, L2, L3 and into DE. So because of course you will have to actually do this inverse, so that has to be then done and multiplied. You get 3 shape functions L1, L2, L3, and these L1, L2, L3 are referred to as actually area coordinates. We call these as area coordinates. I will tell you why. If you look at whatever expression you will get for L1, for L2 and for L3, the L1 can actually be written as ratio of two areas, areas of two triangles. So one here is, so if I again I think let me sketch the element again here, otherwise I will be keep moving up and down. So this is your element, this is your node 1, node 2 and this is node 3, and there is some point P within the element x comma y. So actually L1 you can write as whatever the process is, you get the P inverse multiply with this 1xy, whatever expression you get, that expression can be written as ratio of area of triangle P23 divided by the area of the triangle 123. So you can actually write this L1 as area of triangle P23 divided by area of triangle 1, 2, 3. Okay, so that of course the verification you have to do, invert that P 3 by 3 matrix, multiply, you will get certain expressions for L1, L2, L3. You would see that those can actually be written in this form. Area of for L1, L1 is actually corresponding to node 1 because it is going with L1 into T1 here. So this for L1 it is area in front of that. So P23 in the anti-clockwise sense. Now I am first taking P, then 2, then 3. That sequence you will have to maintain. And if you look at the properties of again these shape functions, that means L1 should be unity at first node, 0 at second and third. L2 should be unity at second node, 0 at third and first node. Similarly, L3 must be unity at node 3 and 0 at 1 and 2. So you will find based on this that when we want to evaluate L1 at node 1 itself, means this point P is right here at 1. So then it is area 1, 2, 3 divided by area 1, 2, 3. So obviously it would be unity. If you want to evaluate this L1 along a line going from 2 to 3, so then point P is lying on this line 2, 3. So area of the triangle is actually 0. So 0 divided by a finite area will give you, area of the triangle will give you again 0. So you will find that L1 is unity here and 0 along line 2, 3. So similarly L2 is given as area of, now for 2 when we write, we take the area in front of the that, so that is going to be P31. Of course you will have to be, you have to maintain the anti-clockwise sequence of the points. So area of the triangle P31 divided by area of the triangle 1, 2, 3. Again you can check the same property. L2 would be unity at node 2, 0 at along line 3 to 1. So similarly L3 is given as area of the triangle. So when you are trying to write for 3, so in the numerator you have area of the triangle in front of that. So P12, so area of the triangle P12 divided by area of the triangle 1, 2, 3. So the interpretation of these, and since these shape functions L1, L2, L3 are ratios of the areas, and therefore they are named as area coordinates. In finite element formulation we call these as area coordinates, L1, L2, L3. So as you see the value of L1 is unity here. So if you look at the values of these area coordinates 1, 0, comma 0, here L1 is 0, L2 is unity, L3 is 0, here L1 is 0, L2 is 0, L3 is unity. So these are the values of the area coordinates of nodes 1, 2 and 3. And if you recall your elementary say algebra, so you would have done coordinate geometry, you would have done say area of the triangle say P23 can actually be written as determinant of 3 by 3 determinant. So first is point P, its coordinates are 1 x y, then point 2 coordinates are x2 y2, and then point 3 coordinates are x3 y3, and of course divided by 2. So area of the triangle P23 can be given by this determinant, and similarly area of the triangle 1, 2, 3 can be given by half of the determinant. 1, 2, 3 means first point 1 x1 y1, 1 x2 y2, 1 x3 y3. So similarly you can write for the other L2 and L3 also, whatever areas are involved, 1, 2, 3 of course there. Similarly you can write the area P31. You have to just maintain the sequence of point in anti-clockwise sense, otherwise you will have mistakes in sign. So this is about the interpolation. About the interpolation functions which we are using as area coordinates here, and of course this is your expression for T. So finally whatever we have got as T is now your in terms of these shape functions L1, L2, L3, and this side you have your DE, and this is as usual we write this as interpolation matrix. So H into DE, that is our standard notation. This is H, and D of course is the same D, T1, T2, T3. If we want to substitute this in integral functional, we need the derivative of T with respect to x and y. So we need to evaluate that. So del T by del x and del T by del y, we need to evaluate this vector. So how do we write that? Del T by del x is going to be, now this is a constant quantity, derivatives of these shape functions with respect to x. del t by del y would be derivatives of these shape functions with respect to y. So, I can write this again in the matrix form both put together, and this side what you have is your T1, T2, T3. So, you will have del L1 by del x, del L2 by del x, and del L3 by del x. Then you have del L1 by del y, del L2 by del y, and del L3 by del y. So, because t is L1 T1 plus L2 T2 plus L3 T3, its derivative with respect to x is going to be simply the derivatives of shape functions with respect to x, and into del L1 by del x into T1, del L2 by del x into T2, del L3 by del x into T3. Similarly for y. So, this is what you will have, and we call this as actually your B matrix as a gradient matrix. So, you can say this is B into DE, and obviously B is a 3 by 3 matrix. This you are calling as BE. Now, before substituting this into the integral functional, let us look at what are these derivatives. So, let me, if I want to evaluate del L1 by del x. So, as per the definition, L1 is area of the triangle P23 divided by area of the triangle 123. So, let us, because that is a constant quantity within the element, area of the whole triangle. So, let us say area of the triangle 123 is equal to, let us say A, that is area of the total triangle is say A. Then L1 is simply going to be del by del x of area of the triangle. So, if you look at by definition, L1 is area of the triangle P23 divided by area of the triangle 123, and area of the triangle P23 is given by 1 by 2 1xy, 1x2y2, 1x3y3. We want to differentiate this with respect to x. So, we would differentiate here you can in case of determinants. So, in case of matrix, derivative of a matrix with respect to a scalar means derivative of all the elements of the matrix within that. In case of determinant is derivative of any one row or column. So, in this case the variable are in the first row here. So, you differentiate that partially with respect to x. So, you will get del L1 by del x as 1 upon 2a, and then the determinant derivative of the first row with respect to x, so 0 because first term is constant, second term is x, its derivative with respect would be 1, and third is y, its partial derivative with respect to x again would be 0, and then this is 1 x2 y2, 1 x3 y3. So, essentially I am arriving at this from this expression. This we already said is a. So, and this area is half of this 1 upon 2a, derivative of this. So, derivative of this with respect to x 0, this is unity, derivative of this with respect to x is 0. So, this is what you get as your del L1 by del x. And if you now just do this open this determinant 1 upon 2a, then what you get is this is 0, this is 0, so only the second term. So, that is going to be you would see that it is going to be y2 minus y3. That is just because this term is 0, so you open this determinant. The way you solve for the determinant, you will get finally this as the del L1 by del x. So, which is simply 1 divided by twice area of the triangle 1, 2, 3 into y2 minus y3, difference of y coordinates of node 2 and 3. Then similarly, you would find that del L2 by del x, you can actually check in a similar manner. So, this is going to be 1 upon 2a, and then the determinant of, because if you look at the as per the definition of L2, we are going with P31. So, that is going to be, of course, the first row will be still 0, 1 and 0, and then if you look at here 3 and then 1. So, you have 1 x3 y3, 1 x1 y1, and this multiplication will give you 1 upon 2a into, again if you open this determinant, what it is going to give you is y1 minus y3, y3 minus y1, because there is a minus sign as the second row. So, we will have y3 minus y1, and actually this follows cyclic order. So, once we have written this, so this is 1 upon 2a, y2 minus y3. Now, 2 you change to 3 and 3 you change to 1 in a cyclic order. So, see if I have 1, 2 and 3 here. So, in this y2 minus y3, there is difference of this minus this. Now, you go one more. So, you will become get y3 minus y1. For the third one you will get y1 minus y2. So, same way you can see that del L3 by del x would be 1 upon 2a. Of course, this is actually simple mathematics. So, this is going to be finally y1 minus y2. So, these are the derivatives. You see that they are in the simple form, that is 1 upon 2a area of the whole triangle y2 minus y3 or y3 minus y1 or y1 minus y2. So, similarly, you also need del L1 by del y, which would be again in a similar manner 1 upon 2a 0 0 now 1, and then this is p2 3. So, 1 x2 y2 1 x3 y3. Okay, it is the same manner. Now, you are taking derivative with respect to y. So, constant derivative is 0, x derivative is 0 with respect to y, this is 1, and if you open this again what you get is x3 minus x2. So, you get 1 upon 2a into x3 minus x2, because this is a first row and third column. So, you get plus, so it is simply the this into this minus this into this minus this into this, which is x3 minus x2. So, similarly you can see that in a cyclic order this would be 1 upon 2a into then x1 minus this is x3 minus x2. So, 3 is replaced by 1 and 2 is replaced by 3, and you can check with the determinant, this is your a, and del L3 by del y would be 1 upon 2a x2 minus x1. So, these are all derivatives. So, you can say that if you substitute all of these into your B matrix, so you can say finally the B matrix can actually be written as 1 upon 2a outside, and then the matrix inside would be 3 by 3 matrix. Of course, first row is the all derivatives with respect to x, which is y2 minus y3, y2 minus y3, then y3 minus y1, and then y1 minus y2, and this is 1 upon 2a is outside, and since this is a matrix, so that means this would be multiplied inside with every element. So, you can write this as starting with x3 minus x2, x1 minus x3, and x2 minus x1. This is your B matrix, so finally written in this form. And now we will have to substitute whatever approximation we got. I think there might be class here, somebody is already at the door. So, now we need to substitute this in the integral functional. The way I have written this integral functional is slightly we will have to rewrite it, so that the matrix vector multiplication is actually consistent. So, this term you can write as T transpose into Qn, and this term can be written as, so then what you do is rewrite the integral functional I again. So, I you can rewrite as first integral, which is cyclic integral. I can say T transpose into Qn ds, and then the domain integral you can write, so plus integration from x1 to x2. Now, see let me this domain integral not x1 to x2, because we are now writing this for the element. So, this integration is then across the element boundary, not the entire domain. So, this integration I will now put over the area of the triangle. So, let me say that this is over the total area of the triangle. You have k by 2 here, and then the del t by del x whole square plus del t by del y whole square can be written as del t by del x del t by del y transpose into del t by del x del t by del y, and of course dx dy here. This a denoting that integration is over area of the triangle. And if you see this is, you take the transpose, multiply this transpose vector with this, you get same del t by del x whole square plus del t by del y whole square, the same term which we have got there. And then the last term we have is in the integral functional, this particular term. So, that also we can write as minus integration again over the area of the triangle T transpose into Qz, which is heat generated inside the element dx dy. So, this is your I. Then what you do is substitute T equal to h into d, and know del t by del x del t by del y b into d, take the variation delta I equal to 0. So, you get finally the element level Gaon equations from delta I equal to 0, and this will give you the intermediate steps are exactly the same. Now I will get here D transpose H transpose, here I will get K by 2 into D transpose B transpose into B into D, here again D transpose into H transpose QG dx dy, and then you take the variation. So finally you will get the same form of the element level equation. So let me still say the coefficient matrix as Ke into De. These steps are same, I am not repeating, and you will have F external, that is because of the heat generation for the element, and plus F internal, that is actually this, because now when you are talking of an element, so this is interaction between different elements, so we let us call that still as F internal for the element. And the expressions for these, now if you look at the Ke would be the integration over area of the triangle, it would be K into B transpose into B into dx dy. So this is what is this K is coming from this. So K by 2 goes, because when you take the variation you have D transpose here, D again, so that 2 gets cancelled half here. So you get K B transpose B dx dy. The concepts, the derivation in between steps, that is now from here to here, are exactly same as what you do in case of 1D problems. There is no difference. And so that is how you can see that this you will get in this form, and if external E it will be, then you can see that is basically coming from this. So again integration over area of the triangle, this would be H transpose into QG dx dy, and the last one is your F internal, which is integration over the area you are taking on the right hand side. So let me put a minus sign here, and this would be H transpose into Qn dx dy. This is boundary integral, I am sorry, this is not the domain integral, but it is a boundary integral. So you have cyclic integral ds. So this would be ds. Now only thing is this contour integration is along the boundary of that element 1, 2, 3, not over the entire domain of the problem. So this becomes your element level governing equation, and actually this is the simplest problem in 2D which you can do further, get the element level matrix and do the assembly and solve problems. So I stop today here, and we will continue in the next class. Actually take some couple of problems where we would evaluate the matrix and vectors, and then assemble and solve, impose a boundary condition, and finally solve for the temperature at node points. So that will continue in the next class. If you have any doubts or questions, you can ask in the next class, outside the class. Thank you.